Hello everybody. So today I will talk about the geospatial indexes again. So I took this video yesterday and day before yesterday, but still I do it again for my own practice sake. I think this should be the finalized version. So I will talk about three indexes. So quad tree, R tree, and GeoHash. Okay, and let me start from why do we need the geospatial indexes first. So typically, in the system design, there are some cases that user would like to know some other users, or I should say restaurants, which are maybe, for example, up to 30 miles from current his location or something. So I can rephrase this question, like let's say user is at XY coordinate 20 and 30, and there are so many points. So these points represent, for example, in Uber, maybe driver's location, and maybe in Tinder, some other users' locations, in Yelp, restaurants' locations. And there are XY, let's say 11, 20, or something like that, 20, 27. So let's say, for example, like this. So this XY 2030 is the user's location, and also the, let's say, driver's locations in Uber. And what I'd like to do is, let's say, I'd like to find the 5 miles away, up to 5 miles away from this user. In that case, X range should be 15 to 25, and Y range should be 25 to 35. Of course, there are some point users, even in this range, there are some drivers who are in this range, but because this range represents the rectangle, and what I'd like to know is the radius 5 miles. So, I mean, there's some users, even if there are some drivers who are, even though they're in this range, in these ranges, actually they're not in the circle of radius 5. But I can filter them easily with database. So I will think about this one first. So how can I get the point or the points which meet both of them? So maybe the quick idea is using the composite index of B tree in, let's say, relational databases. But if I create the composite index with X and Y, what happens is that in the B tree, the node, or I should say, data points are sorted in this way in the leaves. So they are sorted in XY tuple as a tuple. And what happens is that with 1525, I can find the point which is the beginning of the, what should I say? Yeah, from X, I can filter range 15 to 25. So, okay, let me quickly change it. Let me do it. Yeah, so with X, I can filter the range of point in with this 15 to 25. However, after that, Y is not sorted anymore because points are sorted by X, and then in each same X, they are sorted. So now because we have X from 15 to 25, these Y's are not necessarily sorted, which means that I cannot filter the range. I mean, I cannot filter anymore with using binary search, kind of, with composite index. So which means that I have to scan all the data point to confirm they are in these ranges. Sorry, they are in these each of them satisfy the range y25 to 35. So this means that it takes log x time to, reach the first point, and then I have to linear scan. And in the worst case, of course, filtering with x is not so efficient, and most of them are in this range, for example, 15 to 25. In that case, the database engine has to scan almost all the data. So it takes overwhelming time. So that's the kind of point of composite index. So we need the specialized index for location searches. And yeah, that's why we need quad tree, R3, and GeoHash. So now we talk about the quad tree. So quad tree is a tree structure. And what should I say? So in the quad tree, firstly, since there is only one point, and there's a big plane, and the, let's say, points exist in this plane, 2D plane. Firstly, because there is only one node, the database engine prepares only one node, and that node contains the data of that single point. But when there are so many points, let's say in specific area, this quad tree divides that area into 4, and this quad tree index does this subdivision recursively for dense areas, so that each single node contains not so many data points. So I will show you an image. So I will go with this. So in this case, let's say there is only node data point A. In this case, there should be only one node, which is enough. And that node contains the point A. And as there are many points, as the point increases in specific area, let's say in this area, so there are B, C, D, E, and this is too big for this rectangle. So originally, these 4 areas are represented by one node, one single leaf node. But now this is divided into 4, and each sub-area has a corresponding leaf node. And as you can see, the data points are stored only in the leaf nodes. Yeah. Okay. And yeah, also as you can see from this, the division occurs only in the dense area. So let's say in this area, M and OP, this occurred. I mean, subdivision occurred 1, 2, 3, 4 times. Yeah. And this is, this is as a deep, this leaf is deep in the tree. Yeah. So this is a basic idea of the quad tree. And obviously I can say this deep, leaf nodes can become the kind of problem in the performance. So I will write it here. So as a weak point of quad tree, so for dense area, the leaf node is deep. And as I said, this is unbalanced tree. Yeah, of course, because only the dense area is subdivided. So, what's the problem of this deep node? So let's say this is a map, and each point is a restaurant. And let's say this area is New York. New York has so many restaurants, so restaurant data in the New York City are stored in the, nodes deep in the tree. So if user searches restaurant data in the New York City, so if user search area is this to find the data point, the database engine has to go down the path to these reef nodes. And the first problem is it has to, go down so many times in the path. Yeah. And the second problem is when there are so many users in the New York City, the users who search is also there so many. Of course, there are many users who try to know the restaurants in the New York City dense area. So this query path can become the hotspot. Yeah. So that's why I can say this becomes performance bottleneck of the read query. Write that down. Okay. And also I would say another problem is, so this is quite universal to the tree structures, but if the data point moves, let's say here MNOP is very dense, but let's say so many nodes from here to, let's say, around here. So in that case, the tree structure has to be restructured. So when the data point moves frequently, intensively to the distant area, the cost to update the tree is high. So I would say not good at not suitable for a dynamic data. Yeah. So because update query cost high. Okay. So this is the second problem of the quad tree. So maybe I should quickly talk about what happens if I search around this area, MNOP. So from the root node, in this case here, because the search area is this, this is here is a tree, which means that these three subtrees are not our interest. So these are trimmed. And it goes down here. Sorry, I don't have to think of the trimming. I can just say the search area is around here, so I go down here. Yeah. And if search areas also, have the bit in this, top right rectangle, also this has to be scanned. So maybe concurrently, I have to scan all the path which is related to the search area and go down until the reef. So that's a basic idea. Yeah. And of course, if I search for the radius maximum, the point of course, if the point is in the tile, let's say O, there may be some points which are not in the radius. Yeah, because it's the arc, curve. So those points should be filtered out, obviously. Okay, so this is about the quad tree. Okay, so now we talk about the R tree. So R tree is also the tree structure, but the fundamental difference from quad tree is quad tree is built top-down recursively, but R tree is built bottom-up. So I will show you with an example. So let's say I will use this one. So let's say there is some point in the A or maybe B. So firstly, as a premise, I would say data points are stored only in the leaf nodes. So in this case, A, B, C, D, E, F, G, blah, blah, blah. So these gray areas contains a point. And for other white areas, there isn't no point. There isn't a point. And that being said, when there's some point in A, database engine creates a kind of box which contains those points. So this box is, let's just say boundary box, minimum boundary box of the point inside. And then the same thing happens for B if there's some point here. And same for C, D, E, F, G, H. And what happens is that, let's say I'd like to search with this area. So if my concern is this area, I can say the longitude, latitude, or I should say XY range of the search area. And also for this A area, we obviously have the X range, Y range too. It can be stored in the leaf node. So I can immediately say A doesn't have the overlap with the search area according to the longitude, latitude ranges. So I can trim A, and same for trimming B, and samely trimming C. And finally, because I'm searching here, K has the overlap. So I take a look at the data point in K one by one and confirm if there is an overlap with the search area. So that's the idea. But checking each box one by one takes time. So the idea is for box A and B, we think of the minimum boundary box of A and B, which is named N here. And for C and D and E, we create the minimum boundary box named P here. So with this, what happens is that if I'm searching for this area, okay, we have the T. This is the another boundary box which contains, N and P and also Q. So database engine starts from the root node, and because this area, search area, longitude, latitude range doesn't have the overlap with the ranges of T. So I can trim T here immediately. We don't have to take a look at smallest box A, B, C, D, E. So T is trimmed, and I go down to R and S. And let's say R doesn't have the overlap with the search area. Now I can trim R. So S is my concern. So now in S, let's say I'm searching for this around here, K and L has the overlap. In this case, M is trimmed, and the database engine checks the data point in leaf node K and L one by one. So this is the basic idea of R tree. Yeah. So each point is, as I said, the leaf node corresponds to the box which contains the points, and we think of the minimum boundary box of boxes recursively in the bottom-up approach. And maybe one more thing I should tell is R tree is balanced tree. Of course, we can decide how many boxes the parent box should include versus contain. How many child boxes the parent box should contain. So we can adjust the tree structure. So if there are many boxes here, probably the parent box should have many more boxes contained. So in that way, this can be the balanced tree. Okay, so there is one thing maybe I should talk about. So how are these parent boxes created? Or I should say, for example, in this case, the parent box N contains A and B, but of course there's an option that A and C are contained in the parent box cache. So actually this is the kind of optimization the database does. I don't dive deeper into this, but the smart algorithm makes the cost of search and insert minimum. But the bad algorithm of boxing makes the obviously database performance worse. So yeah, I just say database engine does it in a smart way. And okay, so now we talk about pros and cons. So for R3, this is a balanced tree. So this problem in quad tree doesn't occur. So I'd say, because this is a balanced tree, read query performance is stable. Yeah. And also I can say this is good. Because let's say I'm searching for this area. In this case, the areas which, the nodes which is scanned are the point in this area G. So as long as the boxes are created in a smart, optimized way, the data point which has to be scanned to in the box is minimum. It doesn't contain additional data to be checked, which ends up not included in the search area. Okay, but this problem, dynamic data, high update query cost problem is still here, because again this is the tree structure, and let's say many point in G moves to this area. Yeah, we have to create a new box, reef box, and also we have to create the restructure the tree structure, because I have to think which parent box should contain this or something, blah blah blah. So again, this is not suitable for dynamic data when data moves frequently to the long distance. Of course, the data move is only in this area in G, and the move is quite small, it's fine. But if the move is large and frequent, this becomes a problem. Oh, sorry, this is so good. Okay, and I will talk one more pros here. So this R3 can handle not only point but also polygons. So the polygon, what I mean here is like the form of, let's say, California state, or the form of the river, like the stripe or something like that. Yeah, or maybe the form of the park. And so I told that there are many points, but in the data set, but it can be the polygon. So if I have the polygon instead of the data point, what I store in the database index is like the longitude latitude, or I should say, I would assume that the park is like the rectangle. And again, I use the minimum bounding rectangle here too. Again, so I take, let's say, I want to put the park as the data point. In that case, I think of the minimum boundary and store that data inside of the data index. And let's say the park looks like this. And because we have the reef node, which contains that, minimum boundary completely. So again, in the completely same way, I can filter the, reef which contains that polygon. Yeah. So sorry, maybe I should say the premise. So I'm thinking if the polygon, like the park, is included in the search area. Yeah. In that case, that park can be, thought of as the minimum bounding polygon. Sorry, minimum bounding rectangle, and do the same thing. So in that way, instead of the data point, I can use the polygon data, in the data set. And probably what I forgot to talk in this example is, one more thing to be noted is the boxes, aside from the reef boxes, may overlap. So in this case, I can see the box T and U overlap. So this is totally fine. And let's say I'm searching for this area, like, okay. Oh, let's say I'm searching for this area, G and H, around here. In that case, when I go down in the tree, this area is included in T and U. So I cannot trim yet. And I go down to NPQ. And because this is included in the Q only, and N and P doesn't have the overlap, they can be trimmed. And go down from Q, and I found G, it has the overlap. So no data point in G should be linear scanned and checked. And from U, similarly, I go down to R, S, and S is trimmed. And I go down from R to H, and because H has the overlap with the search area, no data point in H should be scanned. So in case of the around this area, I have to take a look at the data point in reef G and H. And in this process, the database engine has to go down from two paths concurrently. So that's something I wanted to clarify here as a side note. Okay, so I will talk about the next one, GeoHash. So as we saw so far, these two indexes, quad tree and R tree, are custom tree structure. But for this GeoHash, actually this is, I can say, in this GeoHash, what happens is that from XY or longitude latitude, it calculates the hash value, kind of, and store it in the B tree index. So it doesn't have the kind of specialized tree structure. It uses the tree structure, but it's old class B tree index. So that being said, I will show you an image, an example. So, okay, I will use this example here. So, first thing I would like to say is, in case of GeoHash, each, area unit kind of block has the same size. So this is different from quad tree and R tree, because for quad tree, the area is subdivided only when it is dense. So the block unit kind of had different size. For R tree, obviously the reef boxes had a different shape and different size. But for GeoHash, the reef kind of, the unit block has the different sizes. And it works in this way. So in GeoHash, the whole area is firstly divided into 4. And then for each sub-area, it is divided into 4 again. So recursively, this occurs for every, tile. So this is the GeoHash, and for each tile, the number, or I should say digit, is given, like 0, 1, 2, 3. And when I subdivide the tile number 2, it has an additional suffix 0, 1, 2, 3. Yeah, and then here it is subdivided, and each of these 4 tiles have another additional suffix 0, 1, 2, 3. So this is how the numbers are assigned. And the thing is, this number is stored in the database as additional column, let's say hash value column. And B-tree index is created based on this hash value. Yeah. So let's think what happens if user queries the, geolocational query. So let's say user is looking for the data point, which is in this search area. Sorry, here. So in this case, the database engine has to take a look at tile 300, and also if the search area is around here, it also has to take a look at 122, or maybe if it's here, it also has to take a look at 123 and 301 also. So according to the center point and the radius, the database engine knows which tiles it has to check. And for each tile, because it has the, B plus 3, database engine can access the first node in this tile, each tile in log n time. And then from there, it linear scans point in those tiles and confirm each point is really in the search area. And of course, these 4 tiles check can occur concurrently. So this is, what happens with the GeoHash query. Sorry, queries on GeoHash index. Okay, so I will talk about the pros and cons. So firstly, I can say read query performance is good, because this is the database can know which tiles to be checked almost immediately from the search range. Yeah, and the table. But I would say R3 is better at performance, especially when the search area is small. This is because in GeoHash, let's say it has to check only this area, and that area is close to the boundary, and it, has the overlap with tile 122. In that case, database engine has to check all the points in 122. So this, I don't say this is the problem if the search area is big like this. Yeah, the area in which every data point is scanned and checked is quite similar to the search area circle. So there aren't so many additional data points to be scanned. But if it is quite small like this, And if it's on the boundary, let's say here, it has to take a look at the 4 tiles. Yeah, which is, I would say, so many additional points which should be filtered out in the end. So in those perspectives, because of this kind of boundary problem, I would say R3 is better at read query performance, but still GeoHash is very performant, I can say. Okay, and another point, this is good for dynamic data, unlike quad tree or GeoHash. This is because when the point is moved, all it has to do is update the x column value, y column value, and GeoHash value recalculated. And updating the data in the B tree costs much less compared to updating the data in the tree structure of quad tree or R tree. So I would say update query cost is lower compared to quad tree and R tree. Okay. But I would say as the con has a boundary problem. Yeah. So this is what I've just talked about. So if the search area is on the boundary, it has to check additional tiles just for the small overlapping area. So I can say that's the con of this GeoHash. I have something I'd like to add about this GeoHash. So in this example, the area is the square or rectangle, and these areas, each area is divided into rectangle, child 4 rectangles. But obviously, this doesn't take the cover of the earth into the consideration. So, to be more accurate and performant with the cover of the earth, there are 2 similar types of GeoHash indexes. The first one is called S2, and this is developed by Google. So S2 considers the cover of the earth into the shape of each tile. And also Uber developed H3. So H means hexagon here. So each tile is shaped hexagon. So this also considers the carving into consideration and performs very well. Okay, so I will quickly review each database indexes, and also I will talk about the use cases. So for quad tree, it divides the area into sub-areas, always 4 sub-areas. And this recursive subdividing occurs only in the dense area. And each area corresponds to the node in the tree structure in the database index. So because this is not a balanced tree, for dense area, the database engine has to go down the path until the leaf node, and it becomes a hotspot. And so read query is not performant for dense areas search. And also, this is not good at the dynamic data, because when the data point moves frequently to far away, it has to restructure the tree structure. So it update query cost high. And for R3, read query performance is very stable and good, because this is a balanced tree, and according to the quality of the kind of boxing algorithm, the data point to be scanned and checked is quite minimum. So this is very good in terms of the read queries performance. But this is not suitable for dynamic data for the same reason as quad tree. And for R3, yeah, this can handle not only points but also polygons. So for polygons data input, R3 just think of the longitude, latitude ranges, XY ranges, and it can handle the point in the same, it can handle polygons in the same way as point data when it handles the read query. And for GeoHash, the read query performance is stable because, how should I say, this is the, actually, this doesn't matter if this is a balanced tree or not. So from the hash value, database knows which point should be scanned in log n time. So yeah, read query performance is good. And this is suitable for dynamic data because, yeah, update query. For update queries, what the database engine does is updates the x value, y value, and also the hash value calculated from x and y. And so the update query doesn't cost that much. But there is a problem named a boundary problem. So if the search area is on the boundary of the square and another square, yeah, database engine has to check both of these, areas. Okay, so this is the con of GeoHash. So now based on this, I will talk which use cases each of these, indexes are suitable for. Okay, so let's begin with the example of Uber. So in case of Uber, the user would like to know where the nearest drivers are, let's say in the 30 miles away from him. So I would use the, GeoHash in this case. Because obviously in Uber, drivers are moving around. So I can say this is a dynamic data. So I don't use the R3 and I go with GeoHash. And for Tinder, in the case of Tinder, the use case is like there is a user who'd like to match with the other users who are maximum, let's say 20 miles from him. So in this case, the Tinder should suggest the users who are within 20 miles from him. So to be honest, in case of the Tinder, I think both of R3 and GeoHash work. Either of them works. This is because even though for Tinder, the data is a kind of dynamic, it doesn't move as intensive as Uber. Because Uber needs a very accurate positions of the drivers. But for Tinder, it doesn't. So as long as the user's location moves, let's say more than 1 mile or 2 miles, it doesn't have to update the user location. Let's say user moves from the house to the nearest park. It doesn't matter in the system-wise. So this is, I would say Tinder is not suitable for dynamic data. And also, in the case of Tinder, the suggested users, or to say stack of suggested users, are not calculated on spot. It is calculated in the, let's say, daily cron job and pre-computed. So the performance for the read query is not so strict. The requirement of the read query performance is not so strict. So for those two perspectives, I think either R3 and GeoHash work. And finally, I will talk about the Yelp. So Yelp has the restaurants in the map. And let's say user searches with the restaurants in California or the restaurants in blah 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 restaurants which are 20 miles away or within from his current location. And obviously, the restaurant data or business data in Yelp is not dynamic. It doesn't move so frequently. So that being said, either of R3 and GeoHash works, but in terms of read queries, R3 is relatively better because of the reason I said. So I'll choose the R3. Okay. So I talked about the use cases now. Okay, that being said, I finished my today's system design practice. Thank you so much. Bye.